Hello and welcome to another video. In this video we're going to be working on create binary tree from descriptions. And in this one you're given a 2D integer array descriptions where you have a description, a child, and an is left. And is left indicates that the parent, that the child is a left node of the parent. So if this is true, it's going to be a 1 or 0. So if it's a 1, that means the child is a left node, and if it's a 0, it's a right node of the parent. So this would tell you here. And then you want to construct the tree from this. So it's kind of a weird question. I don't know, like definitely a weird tree question, but let's get into it. So here, basically, so what you can do, or let's just see like what this is first of all. So 20 has a left child of 15, 20 has a right child of 17, 50 has a left child of 20, 50 has a right child of 80, and 80 has a left child of 19. So if you connect all these, then all you need to know is which one's the root. And so they tell you the root node is a node with value 50 since it has no parent. And then in the second example, so 2 is a left child of 1, and then 3 is a right child of 2, and then 4 is a left child of 3. And the root with, or the node with no parent, so you basically look for like what node is never a child, and that's 1. So that's one thing we can figure out, like what's the root. So root is the node that never appears as a child. So one thing we can do is, like, as we traverse these descriptions, we can just basically store a list, like a set of children, and then we could store a set of all nodes encountered. And then whatever, there's going to be one node that was encountered, but it wasn't in the children set, and that's the one you're going to be returning. So that part is pretty straightforward, but how do you actually build this? So there's a few ways. I honestly thought the most intuitive, so this is what I went with, is you can just make a graph, and the graph will have a key is an integer, so it's like the value of the tree, and then value is the node. And then we can just go through our descriptions and then basically make nodes if we need them. So we can say, like, okay, we have a parent, we have a child, we have a relationship. If we don't have any of these in the graph, let's add them, and then we'll just add that connection. So let's kind of walk through that example for this problem. And then, yeah, I think that's the easiest way. There's like some DFS, BFS solutions, but I think this one's a lot more intuitive in my opinion. So basically what we're going to do is we're going to go through this thing, and we're going to have a graph. So let's just have a graph over here. So here we have this graph, or I'll just leave it like this. Okay, so for the descriptions, actually I think what I can do is this, and then I can write bigger. Yeah, it's a lot better. But for some reason this got down to something small. Okay, there we go. So so we're gonna go through this first node. We're gonna say, okay, so 15 is a child of 20. Well, we don't have 15 or 20 in our graph, so we're gonna make node 15 in our graph. And I guess the easiest way to do it would just be like, instead of showing the graph, I'll just show the nodes. So if the node is, if the node's visible, then that means we have it. So we're going to make a node 15 and a node 20. And so in the graph, this will be represented by like the value 15 is the key, or 15 is the key, and then this is the value. So 20. And then we check which child is it. So 15 is a left child of 20. So we're going to say, like, okay, let's just make a connection from 20 to 15, and let's connect it like this, right? And we have access to these because these are both going to be in our graph. So we know exactly where the nodes are because the key will be the number. So we can say, like, if we want this node, we just access it by looking up the key 20, and then we'll get the node. Okay, so now 2017. So 20 is in our graph, but we have to create 17. And so we're going to create 17. And then we're going to make the connection. So this is a right child because this is 0. So like this. Then 50 and 20. So we don't have the 50, so we'll make the 50. Put it in our graph. And then 20 is the left child of 50, so we'll make a connection here. And that's how we're going to access the tree nodes really easily because we'll just have them all in the graph. So hopefully that makes sense by saying it enough times. Then we have 50, 80, so we don't have 80, so we're going to create 80. And obviously, it's not going to be created like this in the picture. It's just going to be in the graph, right? Somewhere in the graph. And then we're going to have access to these things. And then 80 is a right child of 50. So we'll say 50's right is 80. And then 80 and 19. So that's the last node. So we need to make a 19. I guess this is a little screwed up, but it's fine. So we'll just say we have 19 here. Okay, there we go. So that's kind of what it's going to look like. Now, the last thing you're going to have is you're going to have a set of children. So we're going to take everything that appears as a child and put it into a set. So as we traverse, so like 15, 17, 20, 80, and 19. So we'll have 15, 17, 20, 80, and 19. And basically, then we're going to go through our graph and we're going to say, okay, let's take all of our keys, so all of these keys, and whichever one is not in this set of children, that has to be the parent. Because the root can't be a child. So we're gonna just like let's say we do it in order. So we'll say like is 15 in here? No. Is 17 in here? Or sorry, is 15 in here? Yes. That means it can't be the root. 17, yes. 19, yes. 20, yes. 50, no. So 50 is the root. So we're just gonna return the value in the graph with the key 50, and that will be the node. That will be this node here. And we would already have made all these connections. So I think that's the easiest thing to do is just make a graph with, like I said, the key is going to be the integer and the value will be the tree node. And then we can just make all these connections as we go. And if either the parent or the child is missing from the graph, we just add it to the graph. So let's code that. Okay. So first we'll make a graph of integer to tree node. And we'll call it graph. Then we're going to make a set of children because we're going to go through all the keys in the graph, and whatever is not in the children is going to be our root. Other ways to do this, but since we're already taking event space, we might as well make another variable here. So, okay. Now we're going to go through all of our nodes. So int array node. Descriptions. So we're going to need to get the parent, the child, and the is left. So int parent equals node 0, child equals node 1, and is left. So if the third value is 1, it's left. So we'll just make it a Boolean, and we'll say node 2 equals 1. So if this is true, that means it's left node. Otherwise, it's not the left node. Then we're going to say if the parent node doesn't exist or the child node doesn't exist, let's put it in a graph. So if graph contains parent, then we'll add it in. So we'll just make a new tree node with a left and a right of null, and the value will be the parent value. And the same thing for the child. So graph contains child. Then we're going to add that in as well. Okay. So if there's no parent or the child, let's add it in. Now let's add the child to our children set. Now the last thing we have to do is we have to check is left true. So if it's left true, we're going to make a connection from the parent to the child. The child will be the left of the parent, otherwise it'll be the right of the parent. So we'll say if is left, then graph get parent. These already exist now that because we put them in, right? If they didn't exist, we put them in. So we can just say graph get parent left equals graph get child. So that's how we access the nodes by just using the integer value as the key. And otherwise, it's the opposite. So we can just copy this and replace with right. Okay, so now basically we have a graph of all our nodes, and every node has the connection set up. Now we just have to figure out which node is the parent. So like I said, we're going to go through all of the keys in the graph, and whichever one doesn't appear in the children is the parent, or is the root. The only node with no parent is the root. So for key, so I think graph, I think it's like key set. Yeah, key set. So I guess there's like also values. Yeah, so there's key set values to get all those. So we just want the keys. if the children doesn't have this, this is our root. So we just want to return. So we don't want to return the integer value. We want to return the actual node. So this is just, we can access it by putting in the integer value. And I think we'll get an error here because we don't have like a default return value. So we still need to provide a default return value, even though in reality, it'll always just return here. So here we can just return whatever. So we'll just return like null. All right. Yeah, but this will basically never be reached in the actual stuff. All right, and there we go. So as far as like efficiency, I think there's no way to do it by making just nodes and just connecting nodes without having like a dictionary or a BFS or some other thing. I think this is like the only way. Yeah, so time. So what are we doing? We're going through our descriptions node by node, so that's O of n. And then we're going through our graph node by node, so that's O of n again, because, well, actually, let's think about it. So a description means a connection, right? So the description is an edge, not a node. But I talked about this before. Actually, so, yeah, I think no matter what kind of tree, I think even if it's not like a balanced tree or a full tree or something, the number of edges is always nodes minus 1. So basically the number of nodes and edges will be the same, like complexity. So here, like there's six nodes and there's 5 edges. And that's because in a tree, basically you're always going to have n minus 1 edges. So if you want to connect everything in a graph without having cycles, you need n minus 1 edges. And that's basically what a tree is. It's a connected graph where everything's connected without cycles. So, because if you think about it, like if you have like 1 connected with 2 connected with 3 and so on, you're going to need 2 connections to connect that whole thing. So for n nodes, you need n minus 1 edges. So that means that the time will be O of n, where n is the number of nodes and or edges. It's the same thing. Yeah, so this will be O of n, this will be O of n, where n is the number of nodes or edges, the same thing. And then the space. So we create a graph where we have all our nodes stored, which is O of n, and then we have all our children, which is O of n, because like I said, every single node is a child except for the top, so that's O of n. Yeah, and then what I will do for the companies thing, if people asked, I'll just probably add them to the thumbnail. It's probably the easiest, so people can like look at the picture and see what companies it is. And if it's some random company I've never heard before, probably not gonna add it, like Clary. I don't know what that is. So yeah, but yeah, that's gonna be all for this one. Hopefully you liked it. If you did, please like the video and subscribe to the channel, and I'll see you in the next one. Thanks for watching.